Hi, my name is Raymond, and welcome to Module 9, Relational Algebra. Together with my groupmates, we will be teaching you about what relational algebra is and the operations that we can perform. Also, for every section, we will provide an exercise to test your understanding. At the end of the module, we will give challenges for you to apply what you have learned. Let's first understand what relational algebra is. Relational algebra is a data manipulation language for relational model. It is a procedural language in which user needs to specify how to retrieve the expected data. It consists of a set of operations that take one or two relations as input and produce a new relation as their result. Multiple operations of relational algebra together form an expression. The components of relational algebra includes operands. In algebra, a mathematical operation consists of operands and operators. In relational algebra, the operands are the relations or the variables that represent relations. Operators. This maps relations to relations. Rules for combining operands and operators to relational algebra expression. And rules for evaluating those expressions. For this module, we will be using Relax, an online relational algebra calculator, to facilitate your learning of relational algebra. Relax, we will guide you through the usage of this tool. Go ahead and open the link in your browser. When you first load the Relax calculator, the default dataset is displayed at the left side. On your right side, you can input your relational algebra expression and then execute the query. Let's try to load a different dataset. Click on this part, then let's select the IMDb sample. Now it loads all the relations under the IMDb sample dataset. Let's try to view one of the relations. You can either type actors relation here, or simply click on the actors relation name and then execute the query. Then it loads all the records under the actors relation. There are four types of operations in relational algebra: set operations, unary operations, binary operations, and extended operations. I'll hand you over to Jay to discuss about the set operations.
Thanks, Raymond. For set operations, we will take a look at the different set theory operations available for us. We are also going to check available samples and exercises to be able to understand these operations properly. Please be advised that the topics of set theory will not be covered in this video. Only the operations in set are the subject of this video. My name is Joe Ryan Gauten, and I'll be your thought leader for this unit. Before we proceed, allow me to review some terminologies that we are going to use throughout this section. Set is a collection of anything of the same type. In this section, it will be the tuples and the rows. Tuple is an immutable ordered sequence of values. It is equivalent to row in a relational database. Relation is a group of tuples. It is also equivalent to a table in a relational database. While attribute is a field in a relation or table. Degree is the number of attributes given in a relation. Domain is a data type of value that is only permitted for a given attribute. While union compatible is a relation pair that has the same degree of attributes and each attributes are on the same domain. Set theory operations are the standard mathematical operations on set. These operations are binary operation because these are operated in two relations, unlike unary operation that will be discussed later on this chapter. Set operations has four operations, and these are union, intersection, set difference, and Cartesian product. Let's start with union. A union is a set of tuples from both relation R and relation S. Resulting relation will have a degree equals to the degree of relation R and S, meaning the resulting relation, the number of attributes in a resulting relation is the same of the relations. Is equals to the attributes of the relations R and S. Duplicates are eliminated in this operation. Relation R and S must be union compatible. It is denoted as R union S. So from this diagram, you can see that the result of any union operation is consists of elements of relation R plus the elements of relation S, whereas the duplicates are removed. Let's take a look at an example. In this example, we will have a relation rider and relation client from our user dataset. By visual inspection, we can say that these relations are a union compatible because it has the same degree. Riders has 4 attributes and the clients has 4 attributes. And their attributes are of the same domain. So for example, the rider's type is a type of int and the client's type is a type of int. If you execute a union operation on these two relations, what do you think will be the result? It just combined the relation. Now let's check this example in action via Relax calculator. If you're not familiar with Relax calculator, please watch Raymond's video about the Relax. Okay, so moving on. First, we need to load our dataset. This dataset will be provided to you later. Just copy the contents inside the group editor tab, hit the preview and hit the use group in editor if there is no error in importing. So in your left panel, you can see the 3 relations we have in our datasets. Let's go back to the Relational Algebra tab and perform the union operation. First, select the first relation you want to perform the union, and then from our kitchen sink, select the union operation. Remember to put a space on each side of the operation. Then select the second relation. Hit the execute query and see the result. If you notice that we yield the same result as our example earlier. Now let's proceed to our next section, which is intersection. Intersection is a set of all tuples that belongs to R and S. Resulting relation will have a degree equals to the degree of relations R and S, similar to what a union is. Relation R and S must be union compatible. You must remember that not all relations are union compatible. denoted as R intersects S. So from this diagram, we can expect that the result of any intersection are the elements from R that is present, that is also in relation S. Whereas duplicates are also removed. Let's take a look at the example. So let's use our example from YouTube. If we execute the intersection in this relation, it will yield the result John Cena only, because John Cena is the only records that is present from in both relation R or relation riders and relation clients. Because as per definition of intersection, if it only yield a result that is present on both relation. Let's verify this example in Reacts. So let's clear the previous query. Select the first relation, select the intersect operation from our kitchen sink, and then select the second relation. Hit the execute query if there's no error in your syntax, and check the result. That's simple, right? Okay, so let's move to set difference. A set difference is a set of all tuples that belongs to R but not in S. The order of the operands affects the result. Let's check an example later to see what that means. Resulting relation will have a degree equals to the degree of relations R and S, similar to union and intersect. Relations R and S must be union compatible. It is denoted as relation R minus relation S. So from this diagram, we can see that the results consist of elements from relation R that are not elements of relation S. So from the example, from the previous operations, we have the riders and the clients. If we execute the set difference from in these two relations, what do you think will be the result? So as expected, we are only seeing the tuples from riders relations that are not in the client's relations. So John Cena is present in riders and also present in client's relation, so it was excluded in the resulting relation. What if we swap the position of these two relations? What do you think will be the result? We said earlier that the order of operands in set difference affects the result. If we execute the set difference on these two relations, the result will be much different from our previous one. Yeah, that is because the base relation we use now is the client relation. So the statement is get all the tuples that are from clients but not from riders relation. So we have the Mary, Harold, John. So we can verify this example in React Calculator. So let's remove again the previous query. So as before, select the first relation, select our operation in our kitchen sink, then select the second relation. When we execute it, if there's no error, please verify the result. We have the same result as our first example, right? So let's swap the position. So select your first relation. This time, it should be the clients, our minus operation, and then riders. It's too simple, right? Thanks for the author of this Relax, and we can play along with the set operations correctly, yeah. Then hit execute query, and then we can see the results, right? So there's another operation that we need to discuss, the Cartesian product. Cartesian product has much difference from the first three operations. What are those? Let's have a look. So first, let's define the Cartesian product. It is a concatenation of each tuple from relation R with every tuple of relation S. The resulting relation will have the degree equals to the sum of the degrees of R and S. So if R and S has both 4 attributes, the resultant relation will have an 8 attributes. So we can see that later in the example. The size of the relation will be the product of the tuples of R and S. And this time, it is not required to be a union compatible. Cartesian product is denoted as relation R cross relation S. So from this diagram, we can expect that the result should be each element of relation R is paired with each element of relation or set S. So did you get all the concept of Cartesian product? If not, let's have an example. So from our previous example, we have two relations, drivers and the clients. When we execute the product operations on these two relations, it will yield to a result that is a concatenation of each tuple of riders to each of the tuples of the clients. So as you notice, the John Cena, it iterates from the riders relation, and then each item from the riders relation is paired with of each the tuples of clients relation, right? And their attributes is combined also. Okay. So I think the use case for these operations is when we are performing a join operation from SQL. Let's see it in action. Okay. So riders, let's select the cross join and then the second relation. Hit the execute query and we can see the results. So it is paginated because it's just limited to 10 results each display. Okay. I hope you got all the information about the set theory operations. For any questions, feel free to post it into our forum and we'll happy to assist you. And also Assistant Professor Crisanto will clarify it for us. That concludes our set theory operations. Thank you for watching. But before I hand you over to Raymond, let's have a few exercises to check what you have understood with the set theory operations. Okay, for these exercises, you need to have a knowledge about unary operations or any operations that may yield to another relation such as, but not limited to, select and projection. The prerequisite, you should load the dataset provided in Relax Calculator and then perform, or I think you need to find a set operation or operations that yields to the following results. So A, all the first name and last name of the riders and admin. B, list of clients that are admin. C, list of admins that are not a rider. And D, product riders, clients, and admins. Okay. So the goal of this exercise is to let you know that we can mix and match any operations to get the results we want. So one tip to perform this exercise is to have first the unary operations or at least any other operations. So let's have an example first. So you know what I mean. Okay, from our datasets, let's select the IMDb sample. So let's, for example, perform a union operation on the actors and directors. Or let's swap it. Directors and actors. As you can see, there's an error because directors and actors are not union compatible. So how are we going to do that? By the help of unary operations, let's use the projection and then limit the attributes that we're going to use from the actors relation. So in this case, you need to ID first name and last name to match the director's relation. Right. So as you can see, the error's gone and we can execute the query. Right. Considers it. Right. So happy coding. Okay. So I hope you got your answers for our previous exercises, and I'm showing you the one of the possible answers or the possible solutions for our exercise. Remember that there's a lot of possibilities that will yield the same result, but yeah, this one is the one of those possibilities. I hope you got everything right, and handing you back to Raymond for unary operations.
Thanks, Jay. I will now be discussing about unary operations. A unary operation means that the input of the operation is only one relation, and its output is also a relation. In this section, we will be looking at four unary operations: select, projection, rename, and assignment. The select operation returns a subset of the tuples from a relation that satisfies a selection condition. It is the horizontal filter of the relation, meaning it selects some rows and discards the other rows. The notation for select is sigma, followed by the condition, and then the relation. For the condition, you can use any of the comparison operators including and, or, and like. Let's say we want to select all records with last name ending with beach. So our expression will be sigma followed by last name equals beach followed by the actor's relation. And this is the output. Let's say we want to retrieve all movies in the year 2003 with rank greater than 7. So first we click on the selection, type year equals 2003 space and followed by rank greater than 7 and then followed by the movies relation. Then execute. Now we get all movies in the year 2003 with a rank greater than 7. Next up, projection. This operation returns a set of tuples containing a subset of the attributes in the original relation. If select is a horizontal filter, projection is the vertical filter of the relation. That is, it selects some columns and discards the other columns. The notation for projection is pi followed by the list of attributes followed by the relation. If we want to retrieve only the first names from the actors' relation, we'll write I followed by first name and then the actor's relation. And this is the output. Let's say we want to get the first name and last name of actors with first name equal to Michael. First, let's try to filter the records from the actors' relation with first name equals to Michael. So we do that by clicking on the sigma, then click on the first name, type equals Michael, followed by the actor's relation, then execute. So as you can see, we have all the records whose first name is equal to Michael. Now, we want to project only the first name and the last name attributes. So we do that by clicking on the pi symbol, followed by the first name, comma, last name. Then for clarity, we just enclose this inside the parentheses. Then click on execute. Now we only project the first name and the last name. Rename operation can be used to rename a relation, the relation's attributes, or both. For renaming the relation, the notation is row, followed by the new relation name, followed by the relation that you want to rename. For renaming the attributes, the notation is row, followed by the list of new attribute names inside parentheses, followed by the relation. Lastly, the notation for renaming both the relation and its attributes is row, followed by the new relation name, followed by the list of new attribute names inside parentheses, followed by the relation. Let's say we want to rename the relation directors to producers. We write row, then producers, followed by the directors relation. As you can see, the table name prefix is changed to producers. First, let's load the directors relation. So click on the directors, then execute. As we can see, the directors relation has the following attributes: ID, first name, and last name. Let's try to rename them to director ID, F name, and L name respectively. So in the Relax calculator, it has a different syntax on renaming relations and attributes. So first, we click on the row symbol, followed by the ID. Then to rename it, we either select the right arrow or the left arrow. But since we're going to rename it from old to the new name, then we use the right arrow. Then we type in the new attribute name, comma. Then let's rename the first name. Then click on the right arrow. Then the new name, F name, comma. Then last name, followed by the right arrow. Then the new name, L name, space. Then the director's relation. Then execute. Now we can see that we have renamed all the attributes of the director's relation. Assignment provides a convenient way to express complex queries. it must always be made to a temporary relation variable. The idea is to write the query a sequential program consisting of a series of assignments followed by an expression whose value is displayed as the result of the query. The notation is temporary variable followed by the back arrow followed by a relation or expression. In this example, we first do a select on actors relation where gender is equal to M. Then, we assign the result of this expression to a variable named male actors. Now, we can use the male actors variable and do a projection on it. Let's get the combination of relations actors and movies genres and assign the expression to variable t. After that, we're going to select records whose genre is action from the temporary variable t. Okay, first let's try to project the first name and last name from the actor's relation. So we do that by clicking on the pie, clicking the first name, comma, last name, space, actors, relation. Okay. Then we cross product it with the movies genres. So space, cross join, space, the movies genres. Okay. Let's project only the genre attribute. So click on the pie, then type in the genre space. Let's enclose it with the parentheses. Okay. Then execute the query. So you see that we combine the actors relation and the movies genres. Let's now assign this to a temporary variable called t. So we type in t equals the expression. After that, we're going to select the records whose genre is action from this temporary variable t. So we do that by clicking the sigma symbol, then typing the genre equals action space the variable t, then execute. Now we were able to filter the records having the genre equals to action. In this exercise, we will be using the IMDb sample dataset in Relax. Go ahead and open the Relax calculator and load the IMDb sample dataset. For exercise number 1, you need to find all actors whose name starts with CH. For the second exercise, get the first name and last name of directors whose first name is Stanley and rename the attributes as F-name and L-name respectively. Pause this video and try to formulate your expressions on the Relax calculator. When you're done, play the video to check your answers. Now I hand you over to Mon for the binary operations.
Thank you, Raymond. I'm Juan Gonzalez and I will be talking about binary operations. What is binary operations? Binary operations combines two input relations into one output relation. In this section, we will be looking at four binary operations: theta join, equijoin, natural join, and division. Some of the operations that will be discussed in this section will use selection and projection mentioned in the previous section. Theta join. It joins two relations based on the not equal condition represented by theta. It is also known as conditional join. Here are the sum of the conditional operators. And the notation is, in this example, our condition is PC speed less than the laptop's speed. Let's take a look at PC model 1001. And let's check our laptop relation if there is a laptop that is greater than 2.66. There is none. How about model 1003 with speed of 1.42? The laptop model 2001, 2002, and 2003, and so on, have a speed that is greater than 1.42. So those tuples are included in our theta join. 2001, 2002, 3, 4, 5, 6, and so on. For theta join demo, we will be using database systems, the complete book exercise 2.4.1 dataset. And then our problem is to get the PC that has better RAM than the laptop. In here, we set the condition to PC RAM greater than the laptop RAM. And when we execute that, we'll see that PC model 1001 is greater than laptop model 2003. PC model 1001 has a RAM of 1024 while laptop RAM only has 512. Equijoin. Equijoin is done when a theta join uses only the equivalence condition. The notation for equijoin is using the same relation from theta join. Let's take a look at our example if we use equijoin. Let's start with PC model 1001 with a speed of 2.66. Can we see a laptop with the same speed? Let's move on to 1002. The only tuple that we can see with the same result is 1009, and it has the same speed as 2001, 2004, and 2010. For the equijoin demo, we will be using the same dataset. Our condition is PC RAM equals the laptop RAM, and when we execute that, we can see that 1001 and 2002 laptop model has the same RAM. Natural join. Natural join does not utilize any of the comparison operators. In this type of join, the attributes should have the same name and domain. In natural join, there should be at least one common attribute between two relations. It performs selection forming equality on those attributes which appear in both relations and eliminates the duplicate attribute. The notation for natural join is the, the example is about the natural join of a product and a PC. For the product, we selected all the attributes. As for the PC, we will only get the model and price. As a rule in a natural join, both relations should have a common attribute. In this case, the common attribute is model. Product A produces PC with prices of 2014, 995, and 478. Maker B has 649, 630, and 1049 and so on. The model are 1001, 1002, and 3 for A, 1004, 1005, 1006 for B, and so on. For the natural demo, we will get the product that produce laptop. First, first we project the maker and the model from the product, then we natural join it with the laptop. And when we execute that, we can see that Laptop model 2004 is produced by product maker A, and so as 2005 and 2006 model. For B, it produces the 2007 model, and so on. Division. The relation returned by division operator will return those tuples from relation R1 which are associated to every R2 tuple. The notation is, in this example, we can divide laptop relation with PC. When we divide the laptop with PC, we get the result of laptop models 2001, 2004, 2006, and 2010 because they are the ones with the speed of 2, 2001 with laptop speed of 2, 2004, 2006, and 2010. One thing to notice here is that speed is not available to the result. That is one of the features of the division. It will not include the attributes used in the division. So the result is the attributes model and price. For the division demo, we will use the same dataset and our problem is to divide laptop with PC RAM of 24. Before we divide the laptop with the PC, first we select a PC that has 1024 RAM and we project the RAM attribute. And then we divide it with the laptop relation. And when we execute that, we get the following result. As you can see, these are the laptop that has RAM of 1024, 2002, 2005, 2007, and 2008. To verify that, we can reselect the laptop by choosing the laptop relation and execute the query. As you can see here, laptop 2002 has 1024 RAM, so as 2005, 2007, and 2008. Again, here's the result, 2002, 5, 7, and 8. For the exercises, load the database system, the complete book exercise 2.4.1 and relax. And answer the following question. Join laptop and PC to get the PC that is more expensive than a laptop. Select and project PC with 80 HD value, then divide it to laptop. Here are the answers in the exercises. Next, we will talk about extended operations. I will hand you over to Victoria.
Thank you, Mon, and hello all. Extended operations in relational algebra increases power over basic relational algebra. In this section, we will be looking at 4 extended operations: generalized projection, aggregation, outer join, and outer union. The first operator in extended operations that we will discuss is the generalized projection. This operator is an extension of the operation in the unary operation, which is the projection. But in this case, arithmetic functions can be used in the projection list on certain attributes. The generalized projection has the form pi f1, f2, fn, E, where E is a relation algebra expression, while f1, f2, f3, up to fn are arithmetic expressions. As an example, the following are customers of a credit company. Each has their own credit limit as well as their own balances, depending on their spendings. If the credit company wants to see the money currently consumed by each customer, the formula pi, customer name, credit limit minus credit balance, credit info can be used. As shown in the output, Customer name appears with the difference of the credit limit and the credit balance in our query, which is the credit consumed. Let us see this example in a demonstration using Relational Algebra Calculator. After loading the database of the credit company, let us try our query and see how it works. Click by customer name, comma, credit limit minus credit balance credit consumed. Credit info and execute query. We will see the result of the customer name and the credit they have consumed. Aggregation is the second extended operation in this presentation. Aggregate functions take a collection of values as input and return a single value. The aggregate operations are sum, average, count, mean, and max. Aggregation has the form where the calligraphic G is used to show that aggregation is to be applied and its subscript specifies the aggregate operation to be applied. The subscript grouping attributes can be eliminated depending on the kind of query we want to apply. In this example, a list of employees from different departments is shown as well as their salaries. If we want to get a total salary in each department, we can use the query dept g sum salary prop emp. Dept is a group attribute. Calligraphic G is the symbol that aggregation is used. Sum salary represents the aggregation function, and prop emp is the relation. Applying this query will result to this output. Again, let us see this example in the demonstration using Relax Calculator. After loading our database, we can put our query as gamma dept semicolon sum salary total debt salary prop emp, and then we can execute the query. Now we can see the total department salary per department. Oliver will now take you through to the remaining extended operations.
Thanks, Victoria. I will continue the extended operations part and discuss how outer join works. The outer join is the same as the join operation, but the main difference is keeping the tuples of the relation and padding null to the records that do not have default values. There are three variations for outer join: left outer join, right outer join, and full outer join. For left outer join, we keep the tuples of the left relation, and then we place null values on the right relation that do not have its equivalent value. The right outer join keeps the tuples from the right relation and places the null values on the left relation. And for full outer join, we keep the tuples for both relations, and we place possible null values on both relations. The important point for the symbol is the bracket portion, for this will help indicate which tuples are to be complete. The next slides will show examples of the variations and how the result will look like based from the sample data. The first variation I will show is left outer join. I will be using two relations as our example. Relation A gives the square value of a number, while relation B gives a cube value of a number. When we apply relation A with relation B using left outer join, we can see in the resulting table that the tuples of relation A is complete. Since number 4 does not exist in relation B, the cube value through the left outer join will have an empty or have a null value. The next variation I will discuss is right outer join. I will be using the same two relations as our example. When we apply relation A with relation B using right outer join, we can see in the resulting table that the tuples of relation B is complete. Since number 5 does not exist in relation A, the square value through the right outer join will have an empty or have a null value. And the last variation I will discuss is full outer join. I will still be using the same two tables as our example. When we apply relation A with relation B using full outer join, we can see in the resulting table that the tuples of relation A and relation B is complete. Since number 4 does not exist in relation B, the cube value through the full outer join will have empty or have a null value. And since number 5 does not exist in relation A, the square value through the full outer join will have empty or have a null value. I will now show a quick and short demonstration using the Relax platform and load the PhotoDB dataset. Let's load the employees relation. We see that the employees relation has 7 records and the photographers relation has 3 rows or 3 records. Using left outer join, we will retrieve the employees that are photographers. So we load employees, load the symbol for left outer join, set the condition wherein the person ID of the employee is equal to the employee ID of the photographer's relation. When we execute the query, we see that the result will yield 7 records or 7 rows. Upon inspection of the result table, we can see that the employees relation has complete tuples, while we can see in the photographer's relation that there are some records that have null values. That is due to having an employee ID not existing with the person ID of the employee's relation. Next, I will show how the right outer join works and will retrieve the senior employees that has a bonus equal to their salary. So let's load our seniors relation. In our seniors relation, we can see that there are 2 seniors with their equivalent bonus. Let's load our employees relation. We can see that the employees has 7 records having their corresponding salary. So let's use the right outer join to retrieve the result of having the bonus equal to their salary. So we click on senior, then load the symbol of right outer join, wherein their bonus is equal to the salary of the employees, and we execute our query. the query will yield a result of having 7 records or 7 rows. And when we inspect the result table, we can see that the employees relation has complete tuples, and there are no equivalent records in the seniors table, since we were trying to retrieve the record wherein the bonus is equal to the salary of the employee. And lastly, I will show how full outer join works by loading the Wikipedia Relational Algebra dataset, and we will be using the boat and car relations for our example. Let's retrieve car relation first. We see that car has 3 rows or 3 records, while boat also has 3 records. Now, we will do a full outer join by checking if there's a boat price that is also equal to a car price. So, let's load boat. Load the symbol of full outer join. Set the condition wherein the price of the boat happens to be equal to the price of the car. When we execute our query, we will see that the result will have 6 rows or 6 records. And upon inspection of the result table, we can see that the tuples for both the car relation and the boat relation are included, and null values are placed for non-existing data. So we can see here that there are null values for both the car relation and the boat relation. This concludes the demo for outer join. Next, I will discuss how outer union works. Outer union is the same as union, but also considers the attributes that are common in the relation but are not necessarily type compatible. Thus, outer union is equivalent to full outer join with the common attributes. Let's refer to this slide for an example on outer union. Relation A gives the initial value and max value of a variable, while relation B gives the increment value and initial value of a variable. Based from relation A and relation B, we can identify that the common attributes are value and var based from the column name and data type. We can also see here that the max column is either a string or an integer data. And for the increment column, we see that the data type used for storing its value is integer. When we do an outer union will merge the common columns, and we will be able to see the tuples of both relations with empty or null values being placed to non-existing data, which will be based on the data type. We can also see in the resulting table that the max column have null values since there's no specified data type, while in the inc column, we see that instead of having the null values, 0 is placed because it has a data type. Let's go back to the Relax platform and load the PhotosDB dataset so we can see how the outer union works. So using the outer union, we'll try retrieving the persons that are also salespersons. In order to do that, let's load persons, load the full outer join symbol, set the condition wherein the ID of the person is equal to the employee ID of the salesperson. Upon executing the query, we will see that the result will yield 8 rows or 8 records. And when we inspect the result table, we can see that the tuples for both the person relation and the salesperson relation are included, where the null values are also placed to non-existing data. This concludes the demo for outer union.
Thank you, Oliver. And now it's time for the extended operations exercise. For the instruction of question number 1, load the database system the complete book exercise 2.4.1 dataset in Relax. Question is, using generalized projection, get the total cost of each laptop model after adding 200 pesos for the delivery charge. For question number 2 instruction, load the Wikipedia Relational Algebra dataset in Relax. And the question is, using an outer join with department relation, retrieve the list of employees. Please go ahead and open Relax Calculator and put your query, and come back to see the answers.
Now we have an idea and understanding on how relational algebra is related to database management systems. Before we conclude our discussion and presentation on relational algebra, we will give a challenge for us to do. Load the Relax platform and use the IMDb dataset for the challenge. Let's retrieve the number of movies created by each director that has a movie rank equal or greater than 8 and was shown between 1960 and year 2000. Don't forget to share your answer to the challenge in the discussion board. All the best and enjoy using relational algebra. This concludes the group's discussion and presentation on relational algebra. Thank you very much, and let's continue to enjoy learning in database management systems.